Many developers build features comfortably on their own machines, executing syntax perfectly. But when inserted into the enterprise machine, the entire system fractures. This disconnect often stems from the initial learning environment. A typical tutorial functions as a sterile vacuum, removing technical friction to optimize for syntax acquisition along a predefined path. Professional production environments operate under different constraints. These are chaotic systems where developers must navigate legacy code, concurrent team changes, and unpredictable edge cases, while prioritizing long-term maintainability. Moving between these two environments requires a shift in focus toward formal engineering methodology. This split model highlights the difference. On the left is the tutorial execution, a direct line between the user interface and a local database. On the right is a production architecture, a dense web of overlapping components and parallel branches. Operating within this complexity requires version control discipline, methodical debugging, and architectural foresight. Relying on step-by-step tutorial guidance often obscures these constraints, making it difficult for a developer to survive in a collaborative enterprise environment. Version control acts as the baseline collaborative constraint of enterprise software, serving as an asynchronous communication pipeline for the entire team. In a tutorial setting, a solitary developer often uses Git as a simple file storage system, committing directly to a master branch without external review. In a team setting, this habit leads to structural issues. Developers may bypass branch updates or submit monolithic pull requests that are difficult to audit. An undisciplined workflow. A developer merges a massive block of unreviewed diffs into the main branch, accidentally including sensitive environment files in the payload. These changes pollute the repository, causing an error state that stalls the integration pipeline for the organization. To prevent this, engineers must synchronize their local branch with the main environment before initiating any outbound pushes. This requires a line-by-line review of local diffs to isolate intentional architectural changes from accidental keystrokes or testing artifacts. Professional Git usage is defined by highly contextual commit messages and pull requests that are strictly limited in scope. Ultimately, Git discipline demonstrates whether an engineer can maintain the integrity of their team's parallel work. Production failures in enterprise code typically manifest as systemic mismatches between various layers of the technology stack. Solving these requires a shift from guessing, randomly altering front-end code, to a methodical, scientific debugging process. In this example, an API request leaves the front end and returns a rejected error. Changing code within the UI node will not resolve the issue, as the failure exists entirely outside the local component. Guessing is ineffective against production edge cases, like expired authorization tokens, malformed request payloads, or mismatched API response shapes. It also fails to account for environmental mismatches, such as front-end URLs pointing to staging servers instead of local databases. The scientific debugging loop begins by reproducing the error and isolating the specific failure layer. We trace the pathway from the browser console to the network tab. From there, we verify the data shape leaving the client against the network response. Cross-referencing these against backend logs pinpoints the exact variable mismatch between input and output. This process relies on testing only a single isolated variable at a time to maintain control over the experiment. An engineer who cannot trace failures across the network stack is essentially waiting for a senior developer to solve the problem for them. Evaluating a feature based only on whether it functions today ignores the dimension of time and the certainty of future business requirement changes. A common architectural anti-pattern is the monolithic component. Here, UI logic, API calls, pagination, and state are tangled within a single file. This creates a brittle structure where small changes impact everything, rendering the component unmaintainable. Architectural foresight involves the deliberate decoupling of logic to ensure the codebase can accommodate feature additions. We extract network logic into a dedicated API service layer using standardized data shapes. Complexity is reduced by using specialized tools for server state management. This separation allows modular UI components focused exclusively on rendering. We can then utilize more scalable patterns, such as handling filtering through URL query parameters rather than local component state. Professional architecture also accounts for edge states by explicitly defining loading indicators and error boundaries from the start. It prioritizes security by implementing permission-based action rendering rather than assuming a perfect user experience. Code that is built to survive change and scale defines a completed task. This foresight is what separates a production system from a disposable demo. These three pillars, discipline, debugging, and architecture, form the unified, non-negotiable workflow of a professional environment. Relying on step-by-step guidance is a vulnerability, because enterprise tasks rarely align with existing tutorials. Here is the professional workflow. A complex business requirement passes through a well-separated architectural layer. Next, it moves through a debugging layer, matching data shapes against network logs. Finally, the validated feature merges cleanly into parallel version control without disrupting the main trunk. Syntax knowledge is the baseline for entry. Systemic methodology is the actual job. Enterprise organizations compensate engineers to design, verify, and maintain resilient systems.